All right, so good morning. This question is on angular momentum. I will just quickly explain you what is the situation. You can read the question. Don't worry about the choices. Sometimes, the questions don't have correct choices, but we will discuss. Okay, so let's see the question. The question says there are two masses, one, and this is moving in this direction. The mass is m. Okay, so the mass is m and the velocity is v. It is moving rightwards. The second mass is located here, but it is moving in the opposite direction, and the velocity is again v, and the mass is identical m. Right now, before I start solving, and the position vectors of both the masses is given. So the position vector of the mass 1 is given. The position vector of mass 2 is also given to be R2. What is the chosen origin? A is the origin from which all the measurement is happening. Okay. Now, before I start solving this question, I hope you have read the question. Give it 5 seconds, read it quickly, and then we will discuss. And please don't get stuck and hung up on the answers. We will discuss what is exactly happening. I hope you have read the question now, and I will just reduce the size of the question now so that it's easier for us to discuss what exactly is happening, right? So I will try and keep it as large as possible so that you can still read it. I hope you can still read it. Okay, so it's still hiding the content. So I will just reduce the size and bring it on the corner. Okay, so let's discuss the basic concept as to what exactly is happening in this. Okay, let's go to the basic concept. What's the definition of angular momentum? The definition of angular momentum is r cross p, right? The direction of the angular momentum is perpendicular to the plane of vector r and p. You can see in the question down below he mentions cross and dot. So the dot represents the angular momentum which is coming outwards, and the cross represents the angular momentum which is going inside. Very important, because a lot of students are lost in direction of angular momentum, position vector, so on and so forth, right? So we should know r is a position vector in this expression of r cross p, right? R cross P. What is R? R is the position vector of the point mass with respect to the chosen origin. My point mass is here. One mass is located here. The second mass is located here, right? So, and this is my chosen vector. So when I draw a line from here, right? So this is my vector R. This is my vector R1. This is my vector R2. Okay. I hope you have understood. So I've written origin here. So I'm just removing all this. So this is my A is my origin. A is my origin, right? And let's talk about the second situation. Okay. So the masses are equal. The mass of second body is equal. Okay. So this is your mass 2. I will just remove all of this so that this diagram also becomes clear in your mind. Because this is the way it was given. Right? So you know the direction of R1 and you also know the direction of R2. So, okay. Now, angular momentum as a vector product. We have already seen this. And of course, we can write linear momentum as M into V. So I have written that. And the net expression becomes M R cross V. Remember, apart from R1 and R2, in the question, you're also given the perpendicular drops from the origin, which is the perpendicular drop from A on the axis or in the direction of MV is given to be D1. Right? In the previous question, I told you, linear momentum direction is known. Drop a perpendicular from the chosen pivot point, which is our origin in this case, D1 and D2. So I think the biggest source of confusion could be, if you have to calculate the angular momentum, what are we trying to do? If you see the question is not exactly the magnitude, right? The question exactly, if I enlarge it for you, is all about vector product. So if you see on the left hand side, the angular momentum has been calculated as this, right? L vector. So we are focusing on the vector product. if we focus on the magnitude alone, right, then the perpendicular drops are very, very useful indeed. But we have to write the vector product notation of the system. Now, if you see that, let's discuss this, right? So the angular momentum of the first body, okay, which is A R1, right? So if I have to write this, this is the way I will write. This is my angular momentum. And the angular momentum direction, how do we decide it? Before we do that, let's discuss how do we decide the direction of the third vector in a vector product. If you're given A and, sorry, this is your A, this is your B, you have to find A cross B, move from A to B, like this, right? If I move like this, I will go inside. So my answer will be A cross B. Yes, right? It will be A cross B and it will be inward, which means I will draw cross here. Sometimes in the questions, the directions are shown like this. B is shown like this and A is shown like this. You cannot take a vector product in this case. The way to take vector product is the tails have to be at the same point. So I will shift this A here and take it here, right? So A. So this is your A and the angle between them is theta. So look at this question now. Let's do a comparison. My R is going in this direction, right? My R is going in this direction. My linear momentum P is rightward. This is my R1, right? Because I can't use this as a position vector. The direction is determined by when the tails are in the same place, right? So this is R1, right? Cross, I have to do this from R1 to P. I'm moving from R1 to P like this. So this is outward, right? So my LA, the angular momentum of the first mass, okay, with respect to the origin is now M and it is outward, right? So I've written that. Let's calculate the angular momentum of the second mass, 2. Again, the vector is in this direction. This is my R2. This is my V. So I will move like this. My linear momentum is in this direction. So I have to move like this, right? So how do I write this, right? This is going inwards. So R, so it is M R2 cross V inward, right? My angular momentum is inward here, right? So my L2 is coming out to be inward because my angular, the position vector is like this. My linear momentum is like this. I am moving from R to P like this, right? So the screw closes and it goes inside, right? Which means this will be a cross, right? If I have to find the resultant angular momentum of the system, right? So choice number A, if you notice, right? It is correct. The choice number 2, right, says it's a, I think it's a dot which is given for the A also, which is wrong. Okay, the direction of angular momentum for the body 2 is inward. If I have to calculate the resultant of these two, how do I write it, right? Vectorially, I will write it as L for the system is given by, and which is bigger, right? The bigger of the two is R2. R2 is bigger. So magnitude of R2 is going to be large, right? So I will write the inward one first. So M R2 cross V. This is inward. And let's say the notation says that the outward one is smaller. So we will subtract it. Minus MR1V, right? So this is outward, right? This is inward. This is outward. And this is the vector notation, right? This is the correct answer. So don't worry about the answer number 3. I think they have added both, thinking that the vector product, the way they have taken the vector product is not correct. The vector product has to be taken from R to V. If If you move from R to B, you're going inside. If you're taking R to B here, you're coming outside. The correct answer is MR2V minus MRV. The net angular momentum is inward because R2 is very long. For the same linear momentum, the position vector of the second mass is longer, and the position vector of the first mass is smaller, right? You can see, make out from the figure. If not, still this is the correct way to express the answer of the given choices. So all the choices are wrong. The fourth choice, why did we use D? And I mean, I could have used that also, but then the position vector, the angle should have been 90 degrees, right? For perpendicular. But if I know that there is an angle between the two, which is, let's say, this particular one, right? So the linear momentum, so this is the angle between them, right? So this is my R1 and this is my P. So my R1 is going like this and my P is going like this. There is an angle between them. And so is the case here, right? So this is R and this is P. So there is an angle between them, right? So I can't use just straight away a perpendicular drop. I can use that, but then I will get the value of the magnitude, right? Only the magnitude, and I can express D in terms of R2 also, right? It is, if this angle is known to me, right? This angle is theta, then obviously I know this is 180 minus theta. This is 90 degree. I can find this angle also, right? If I find this angle, I can find the base of this triangle, right? A, maybe this is O and this is B. So AOB, this is the base. I can find D2 in terms of R2. But then I will get the answer as R2 cos theta, right? Because the length of the D is R2 cos theta, something like that. I have not calculated this value using the right angle triangle, but you will get it, R2 sin theta or something like that. So be very careful. I think the tricky part was one. I think the answer is wrong. Second is the which one to choose. Whether do we use a vector notation answer or do we directly blindly apply the concept of perpendicular distance? You should not apply. You should apply since the vector notation has been used, focus on vector, not on the magnitude aspect. Because D, in fact, doesn't give you any idea about R, the position vector, which is the hallmark of a vector product question, right? So vector notation, use vector product oriented answers. If it's pure vanilla, the concept of magnitude, perpendicular drop is good enough. But then even the D should have been given in terms of R2 somehow, because there is an angle between them. It's not exactly 90 degrees. So D can be expressed as one of the component of R2 and R1, D1 and D2 respectively. So I hope you enjoyed this question. Please don't forget to subscribe to this channel. Join the community. Thousands of questions being given to the students so that they can work on them, practice, build conceptual understanding, and score high in the examination. Thank you very much for your time today and look forward to seeing you.